So as the first step, let's look at series. So what does series means? So when resistors are in this order means if they are one after the other. So you can see in this diagram, they are one after the other, right? So these resistors and also the battery are in series. So what is special about the series resistors? So let's first draw the current going through the diagram. Okay, so I'm going to draw the current. So this is a battery. So we know in a battery, current starts flowing through the positive terminal. So it goes from this side like this. So there is only one path for the current to flow, right? There's only one path for the current to flow. Therefore, the current through the battery, which is I, is same as the current through each of the resistors. So it is the same current which goes through the whole circuit. So when the resistors are in series, same current goes through all of them. Okay. And now let's assume that this battery is 9 volts. Okay, I just gave a value just to explain it better. Let's say this is 9 volts. So what does this 9 volts mean? So this side, which is the positive side, is 9 volts higher than the negative side, right? That is what is meant by 9 volts. 9 volts is the potential difference. Potential difference. So if this side is plus 9, this side should be 0. That is what's meant by 9 volts, right? Okay. So this is 9. And what can you say about the voltage here? So at this point, it was 9. Right? At this end, it was 9. What about the voltage here? It should also be 9, right? Because we know there is no voltage drop through these connecting wires. These are just connectors. These are connecting wires. Through connecting wires, no voltage drop. But voltage will drop through resistors. So when current goes through a resistor, we know Ohm's law. What is given by Ohm's law? Ohm's law says voltage drop through the resistor is given by current through the resistor times the value of the resistor, right? This is Ohm's law. Ohm's law gives you the voltage drop. So this word is very important. Why? Because voltage drops when current goes through a resistor. So if this is 9 volts here, the voltage here will be lower than 9. Why? Because current flows through this, right? And the voltage will drop by I times R4 because the value of the resistor is R4 here. And the voltage right here, right after your resistor will be 9 volts minus I R4. What about the voltage here? It will be another I times R3 lower, right? So another I R3 will drop through this resistor. Then through this resistor, another voltage drop will happen and it is given by I times R2. And through this, again, the voltage will drop. And that drop is given by the Ohm's law. It is I times R. Okay, so when that happens, so it was 9 volts here. It drops through each resistor, and when it comes to this end, what should the voltage be? It should be equal to 0, because see, this side is 0, right? So through each resistor, there will be a voltage drop. So are you okay up to that point? So if I ask you to find the voltage drop across this resistor, what you would do is you find the current through the whole thing, and then you multiply, you do this. So this gives you the drop, right, through this resistor. Okay. So we will learn more about this when we start problems. So for now, I'm going to erase all of this. So we previously saw that the current which goes through the circuit is the same. So that is a characteristic or one of the properties of series resistors. Same I. Another thing that I want you to know is to calculate the equivalent resistance. How to find the equivalent resistor? So what is the meaning of an equivalent resistor? So from the name, we can kind of understand it, right? So what is the resistor that you can substitute instead of all of this? So instead of R1, R2 and R1, R2, R3 and R4, can you just put one resistor? So that is your equivalent resistor. So this equivalent resistor R, EQ can replace these 4. It does the same job as these 4. So in a series, when the resistors are in series, your equivalent resistance is given by this equation. It is very easy. You just add them together. You can just add the resistors together. So if you had 1000 resistors, you would add all 1000. So are you okay with this equation? I'm pretty sure you have seen this in the lecture. Okay. So I hope you're okay with this. And can I go to the next slide? Yes. Okay. Okay. Here I have an example circuit. So I want you to try part A, B, and C as soon as you can and tell me the answers. So let's try to save time because there are very interesting problems at the end today. So these resistors are one after the other, right? That means they are in series. They are one after the other. And they share the same current I, right? But the current which comes through the battery has only one path to travel. So same I. So they're asking the equivalent resistance. So we know we just have to add the 3 resistors, but they are in kilo ohms. So your answer will be in kilo ohms. So when you add them, your answer is 18 kilo ohms. In the next part, they ask you to find the current through the circuit. So what we have done here is we have replaced all these resistors using one resistor. That's what we have done. And it is 18 kilo ohms. So we can apply Ohm's law, right? The voltage across the resistor, which is 9 volts. So we can just apply the Ohm's law. Voltage is 9. Current is what we need to find. And R is 18 kilo ohms. Kilo 10 to the power 3. So when you do this, you get 9 divided by 18 times this. So 0.5 10 to the negative 3 amperes. Don't forget the sign, okay? Don't forget this thing, kilo ohm part. So your current is fine. And in the next part, they ask, what is the voltage at 2 if the voltage at 1 is 9 volts? So what they're saying is the voltage at this position is 9 volts. So we anyway know it, right? Because in the battery, this side is positive. So this side is 9 volts. This side is 0, right? So what will happen at position 2? That's what they're asking. What is the voltage at position 2? So we know when current flows through this resistor R1, voltage drops, right? And that voltage drop is given by current which is flowing through the resistor times the value of the resistance. So this is the voltage drop across R1. So the voltage at 2 is 9 volts minus this voltage drop, right? IR1. So voltage at 2 is 9 volts minus this voltage drop, which is I times R1. So 9 minus current is 0.5, 10 to the negative 3. R is, what is the R? R is 3, right? 3, 10 to the power 3. This is amps, this is ohms. So I converted kilo ohms to ohms. So when you calculate this, you get 9 minus 1.5, which is 7.5. So here are 2 problems. These are conceptual ones. I want you to do them and tell me the answer. 2 or more resistors are connected in series to a battery. So let me draw it. 2 or more. I'll just draw 2, okay? So when it's like this, we know the current through everything in the circuit is the same. Why? Because there's just one path for the current to flow. So they are saying the total voltage across the combination is the algebraic sum of the voltages across the individual resistors. Something very long. So what are they saying? The total voltage across the combination. So this is my combination of resistors, right? So I have 2 here. So voltage across them, what they're saying is the sum of the voltages. It's true, right? So we know this, if this is like 9 volts. This is same as 9 volts, and we get it by adding the individual voltages of each of them, right? So the voltage across the first resistor is I times R1. So voltage across this resistor is I times R2. We know when we add them together, it should be same as this 9 volts, right? That is what we've been doing in the previous part through voltage drops. So when we add all of them, it should be equal to this 9 volts. That is why when they drop through each resistor, it adds up to 0 at this end. This is 9, this is 0. So this part is correct. B. Same current flows through each resistor. That we definitely know is correct. Because that is the definition of series, right? Same current flows through all of them. Then part C. The equivalent resistance of the combination is equal to the sum of the resistances. We know that also. We know our equivalent is given by the addition, right? If we have 2, we just add the 2. If we had 1000, we will add all 1000 terms. So your answer is D. All of them are correct. So when resistors are connected in series, so this is when resistors are connected in series. Part A. The same power is dissipated in each one. Is it correct? Can you tell me the power equation? So since we have I and R, let's write it with I and R. So I'm going to substitute for V using V equals IR. So I get I squared times R. So you all know these equations, right? These were in your formula sheet, even for the previous exam. So although I is the same for all the resistors, R changes from resistor to resistor, right? So when R changes, power should also change. So this thing is wrong. Power dissipated will depend on the resistor, value of the resistor. If resistance is different, your power will be different. So I use this equation to figure out part A. The second one, the potential difference across each is the same. To find the potential difference, in other words, voltage drop, we used V equals IR, right? Ohm's law. So although the current is the same, we know resistors can be different, right? There's no must to have the same resistance. So resistors can be different. If your resistors are different, voltage drop will be different. So potential difference across each of them will depend on the resistor. So it is also wrong. Part C. The current flowing in each is the same. That is correct. Because we know when it's in a series, it's one after the other and the same current flows through the whole thing. So D is useless. More than one of the given answers is true, is wrong. Okay, so are you okay with this? Okay, so let's move to the next one. So in the next one, We have 3 problems. It's little harder than the previous one. Still the resistors are in series. Do it and tell me the answer. 3 identical resistors are connected in series. And they say 12 amps flow from a battery. So let me draw the battery also. So if 12 amps flow from the battery, through the resistors also, the same 12 amps flow, right? Because we know throughout the circuit, we have the same current. So no matter how different your resistors are, you always get 12 amps because the current through the battery is that. So the second one. So second one is the hard one. And I see different answers for the second one from you. So I see A, B, C. So I see all A, B, C answers. Let's see what's happening. So they are talking about the power source, right? They are talking about the source. Source is a battery. It is a nice single battery. And the power of a battery is given by which equation? This, right? P equals VI. Why cannot we use the other power equations? There are other power equations too, right? I squared R, V squared OR. So why can't we use these two? Because these gives you the power dissipated through a resistor. Because can you see this has this R in it? So for a battery, there is no R, right? There's no resistance for a battery. Therefore, we have to use this equation for the power. So that is fine, right? So we have figured out which equation to use. Now let's see what's happening. So what are they doing? They are going to increase the number of series resistors. So we know equivalent resistance is given by the addition of each of the resistors. So when you have more and more resistors, what's happening? What will happen? Your total resistance increases, right? So when they add more resistors to the system, your total resistance increases. So you're okay up to here? Yes? Okay. Now let's look at the current. An Ohm's law gives you the current through this. And we know the voltage is a constant, right? See, they say the voltage of your power source is a constant. Usually through a battery, the voltage is a constant value. So when your R increases, what will happen to the total current through the circuit? What's happening? If R increases, I decreases, right? I decreases. It makes sense, right? R means the barrier, the resistance to the current. So when the resistance increases in the circuit, the current should decrease. So current is decreasing. Okay, now we know what's happening to the current. Let's go back to the original equation, the power equation. So in the power equation, we know voltage is a constant. Why? They have given that your battery has a constant voltage. So when I decreases, what should happen? Your power decreases, right? So when I decreases, your power decreases. So your answer should be B. In other words, like when a lower current is drawn out of your battery, less power is consumed. See, when the current flowing out of your battery is low, less power is consumed. It puts out less power. So you can use the battery for a long time because it dissipates little amount of power. Okay, now let's go to the last problem in this. Okay, so I got a question. But in a series circuit, wouldn't I stay constant? Yes, I will stay constant in a series circuit, but in this problem, it is it is a changing problem, right? So it's not a nice problem with a fixed number of resistors. They are adding resistors. So initially you can think there were 2 resistors. Now they have put 3 resistors. Okay, so this is not a simple problem. They are increasing the number of resistors in the system. Okay, so in this one, 4 resistors are connected in series. So we can get the equivalent resistance, right? Req is given by 12 plus 3 plus 5 plus 4. When you add them, you get 24. 12 plus 3, yeah, 24 ohms. So now what you have is, you have one resistor which is 24 and it is connected to a battery of 12 volts. They are asking what is the current through the battery. V equals IR. Voltage across the equivalent resistor is 12. Resistance is 24. So you should get 0.5 amps. So everyone who gave me the answer got it correct, right? Yeah. So are you okay with these 3 problems? Yes. Let's move. Now we go to the next part. Parallel resistors. So what is happening in this parallel thing? So let's do the same thing that we did with the previous problem. Okay. So this is a battery. Therefore, we know current should flow this way. However, this is different from the series, right? Why? Because there are multiple paths that the current can flow. It's not single path, right? It's not just one way. It is like this path is dividing into so many paths, so that current will start going through each of them. So let's see what's happening. So current which comes through this, what will happen to it at this junction? Some of will go this way and some of will go this way, right? So I will call the part which goes through R1, I1. So I'm using nice symbols, I1, R1. So I'll call this I prime. So I prime plus I1 is same as I, right? So this I just got split up into 2 parts. So now this I prime comes in this path and suddenly it sees 2 different paths again. So what should happen here? Again, part of will go this way and another part will go this way, right? So I will call the part which goes this way I2 and the part which goes this way, I will call it I3. Okay. So let's see what's happening. So I3 will go through this, right? R3, I3. This is the only path I3 can take. It will go like this. So still I3. And what about I2? I2 will go through the R2 resistor and we'll join this join this I3 at this junction, right? So now they will combine together. I2 plus I3 will start flowing in this direction. So what is I2 plus I3? It is same as I prime, right? You remember that I prime is the one which divided into I2 and I3, right? This is same as your I prime. Okay, so at this junction, what happens? Your I prime and I1 will get combined. So here you will have I prime plus I1 going in this direction. So what is I1 and I prime? It is same as I, right? I is the one which divided into I prime and I1. So this is same as I. So what goes will come back to the circuit towards the battery, but the important thing here is different currents flow through each of the resistors. Can you see it? This different from series. In series, the same current was going through each of the resistors, right? But here, different currents are going through the three resistors. So are you like slightly okay with this? That current splits and stuff? So you're okay that it's not the same current, right? Okay. So I'm going to clear this. So we will learn about this current split stuff more when we go to the next part of the lesson. But for now, this is enough. Okay. So the next thing that I want you to look at is the voltage. So let's again say that this is a 9-volt battery. So if this is 9 volts, this side is 9 volts, right? And this side is 0. So if this side is 9 volts, what is the voltage here? Tell me in the chat. What is the voltage here? Yeah, it is 9. What is the voltage here? 9. What is the voltage here? 9. Why is it 9? Because we know there is no voltage drop across wires, right? We know even in the previous one we learned that there is no voltage drop across wires. So this position is exactly same as this point, this point, this point, anywhere up to here. Let's do the same thing for this side. What is the voltage here? 0. 0, right? So it is connected to this side, the negative side, this side of the battery, which is 0. If this is 0, this is also 0. No voltage drop across wires. So now what can you say about the voltage across each of the resistors? Can you see that the voltage drop across each of them are the same? They all of them are having same 9 volt difference. So the special thing about parallel circuits or parallel resistors is that they have the same voltage difference. If they have the same voltage difference, they are parallel They are parallel to each other. Okay. So in problems, they draw things very nicely. When they draw it this nicely, you can just look at them and tell this is parallel, right? But sometimes they can confuse you and draw very weird circuits. So you have to tell me whether these stuff are parallel to each other. Okay, let's say this is still the same battery, 9 volts. Okay, so there are two resistors, R1 and R2. Are they parallel to each other or not? So I just drew it in a weird way just to confuse you. So how do we determine if things are parallel? We look at the voltage across them, right? So here, this is 9 volts. So both of them have 9 volts this side, right? This side is 0. This is 0. What about this side? This one. This is just a wire, right? I have drawn a long wire just to confuse you. There's nothing happening here, right? Up to here. So this point is same as this point. You can just kind of hold this point and bring it here and just keep it close and see. Can you see that they are parallel to each other? So it is same as R1 like this. And if I just shorten this wire, it is like this, right? R2. So if I drew it nicely, you know it's parallel. So they might not draw things nicely all the time. They might confuse you with this sort of stuff. But you know what to do now. You have to look at the voltage. Okay. So you're okay with this, right? So similar to the series resistors, here also we can have equivalent resistance. So what is equivalent resistance? A resistor that we can use to replace all of this. And it is given by this equation. So it is little different. It is 1 over the equivalent resistance is equal to 1 over R1, 1 over R2 plus, if you have 1000, you would do the same thing for all the 1000 resistors. So we don't like this inverse stuff, right? It's just hard to work with. So to make our lives easy, let's use this equation. Same thing, I'm writing it in a different way. So you do the same thing that you always do. You write the same thing and take the inverse. Okay. So let's use this equation because this is easier. So here is another important point. So this is something that we usually gain from experience. After doing like a lot of sums, you will learn this, but I will state it right now. So the REQ for a parallel circuit, for something like this, for parallel stuff, is always smaller. So this is the smaller symbol. REQ is always smaller than the smallest resistor in the combination. Okay, so your final resistance, your equivalent resistance is always smaller than the smallest one. Let's say your smallest one was R3 in this one. So your REQ should have a value smaller than R3. So you can have that in your mind to compare whether your answers are correct. Okay, so let's go to this problem. So this is a learning problem. So just like the previous one, try to do this as soon as possible and tell me the answers. Find the equivalent resistance. We know these signs, they are parallel to each other. Therefore, we can do this. REQ is equal to 1 over 10 plus 1 over 2 plus 1 over 1 and take the inverse. So when you do that, you should get 0.625 kilo ohms, right? So can you see that this value is smaller than the smallest? So your smallest was 1 kilo ohm, right? This is smaller than the smallest. Okay, so in the second part, what is the current through the battery? So what we just did was we replaced all of these resistors by this one single resistor. So we can just apply V equals IR to get the current. Voltage is 9, REQ is 0.625 kilo. We have to convert it. So we should get, so I'm just copying your answers, 0.0144 amperes. So you will get 0.0144 amperes or 14.44 milliamp. 14.4 milliamperes. But amperes answer is fine. You can just leave it at amperes. So next part. What is the current through each of the resistors? So we just found the total current, right? So we just found the total current which will go through all of them. We don't need that for part C, but we need the individual currents. We need this I1, I2 and I3. We know that the voltage difference across each resistor is 9 volts. Because that is the definition of parallel, right? It's always 9 volts between each of them. So for the first resistor, I can just apply V equals IR to find current. So current through the first resistor is given by voltage across the resistor divided by the resistance of the first one. In the same way, we can do it for the other two resistors. So V is 9 divided by 10 kilo ohms. So you get 0.0009 amperes. For this one, you divide 9 by 2 kilo ohms. So you get 0.0045 amperes. This one, you divide 9 by 1 kilo ohms. So you get 0.009 amps. So these are the three current values that go through the resistors, and if you add them, if you add I1, I2 and I3 together, you should get the total current, right? So when you add them together, you should get this value. So whatever the current which came out of the battery was divided among these three, right? That's what happened. So when you add the 3, you should get I. Okay. So I will move to the next one. So there are 2 problems. First one is easy. It's a conceptual one. Second one, it's a little hard. But it's not really hard. You can do it. When resistors are connected in parallel, so let me draw it. So I'll draw 2 resistors in parallel, okay? So if current I goes this way, it will split up into I1 and I2. So same current flows in each one. Wrong, right? We know the current is not the same because the total current will split up and go through this according to the value of the resistors. So it will depend on the value of the resistors. More current will go through the small resistor, and low current will go through the high resistor. So we know this is wrong. The potential difference across each is the same. That is correct. That is the definition of parallel, right? They have the same potential difference between each other. They have the same V. Part C. Power dissipated in each is the same. So power. So I'm going to write the equation which has voltage and resistance, because we know voltage is common to all of them. It is V squared over R, right? The power equation which has V and R. Voltage is common to all the resistors, but R can be different, right? So when R changes, your power will change. Higher R will result in lower P. Lower R will result in higher P. Okay, so when R changes, your P changes. So power dissipated in each is the same. Wrong. It will depend on the value of your resistor. Their equivalent resistance, so they're talking about Req, is greater than the resistance of any one of the individual resistances. Wrong, right? We know that Req is even smaller than the smallest resistor. So this is wrong. So this part. So your answer is correct, D. A 22 ampere current flows into a parallel combination. So let's see, this is my parallel combination. There are 3 resistors. So 22 goes in. What are they asking? They want us to find the current through the 12 ohm resistor. So let's say this is my 12 ohm resistor, 12, 6 and 4. So if we know the voltage across 12 ohms, we can find the current. So using V equals IR, we can find the current through 12 ohms if we know the voltage across them, right? If we know the voltage, we can just divide the voltage by 12 and get the current. But the problem is we don't know the voltage. So I'm going to find the voltage. So to do that, I'm going to use the information they have given. So as the first step, I'm going to calculate the equivalent resistance. 1 over 12 plus 1 over 6 plus 1 over 4. So this gives me 2 ohms. So when you do that, you will get 2, and we can see this value is smaller than the smallest, right? So now your circuit is something like this. This is 2 ohms and 22 amperes go through it. Now you can find the voltage, right? You can find the voltage across this 2 ohm resistor, which is the equivalent resistor. So using V equals IR, so I'm going to use the equivalent resistance, which is 2, to calculate the voltage across the resistor. So I get 44 ohms, 44 volts. So now I know the voltage across these two ends, right? So we just found the voltage across these two ends. Now we just have to plug it in this equation. Voltage is 44. We want the current through the 12 ohm resistor. So when you divide 44 by 12, your answer will be 3.7 amperes. So your answer is D. So this looks complicated, right? It is looking hard, but it is not hard. So you know how to get the REQ. You know how to calculate REQ for series and parallel separately. Now this is an actual circuit which can have both of them together. There are series stuff, there are parallel stuff together. So in this problem, we are going to find the equivalent resistance between A and B. So let's do part by part. Part by part means when we get problems like this, we do small part first and then go to the next. So can you all tell me which part I can start simplifying? What is the easier point to start? So I got an answer. So I got 2 answers. Yes, we can start from those 2. So we can simplify these 2, right? They are parallel to each other. So they are parallel to each other. What we can do is we can substitute or replace these 2 by just one resistor, right? So this is our first step. We are going to find the RAQ of 42 and 75. 1 over 42 plus 1 over 75. So tell me the answer you get. So 26.9. Okay, now I'm going to redraw the circuit by replacing this part. So instead of 42 and 75, now I have 26.9 ohms. And I have this 33. So I have the rest as it is. I have only replaced these two, 42 and 75. So you all have to tell me my next step. What should I do? Yeah, I got all correct answers. So add the 3 on top. So these 3 are parallel, are in series, right? So these 3 are in series. So let's replace these 3 by one resistor. So I'm going to add these 3. They are in series. Series means you just add the 3, right? 26.9, 33, 61. What do you get? 120.9. Okay, so I'm going to redraw the circuit again with the replaced one. So instead of these 3 resistors, we can just have 120.9 ohms. This is 10.5. What is my next step? So parallel 120 and 10. So you're asking me to do this, and I'm going to do that. So we are going to add the two. They are parallel. So the equivalent resistor of those two is 1 over 120.9, 1 over 10.5 inverse. Tell me the answer. You are very quick. 9.66. Okay, 9.66 ohms. So now I have this. This is my A and this is my B. I have 9.66 ohms and 35 ohms. I think this one I can manage. So there are two resistors. They are in series, right? So we can just add them. So finally, we have one single resistor between A and B. And that is 44 point, I'll write 44.7 ohms. And that is your final answer. So you do this till you only have one single resistor, and that is your equivalent resistor, right? So here we have another one. Now you all are going to look at this very carefully and tell me where to start. Yes, I got an answer series. Yes, correct. Which two? What are the two in series? 105 and 84. Correct. So these two are in series, right? Although they have like drawn it in this square shape, they are actually one after the other. So they are series resistors. So let's start with that. So REQ, since they are in series, we can just add them, right? 105 plus 84. Um, 105 plus 84, what is the answer? 189, 189. So I got another answer in the chat saying 84, I think 84 and 42. Let me check. Yeah. So what is the problem with 82 and 42? Why can't we just add them in series? So if you remember, series means same current flows through them, right? So here we have another junction. So that is why we cannot add this and this. So when we have another junction here, they don't have the same current, right? This one and this one may not have the same current because some current will go through this, right? So for resistors to be in series, they should have the same current flowing through them. Okay, that is why these two were in series, same current, right? See, whatever comes through this goes through this. 189. So I'm going to redraw this. This is my A. Oops, and we have this 42 and we have a 21 and B here. We have a 63 and instead of these two, we have one resistor, right? And this is 189. I know my diagram doesn't look nice, but it will do the job for now. Okay, what is the next step? What are the two resistors we can kind of solve? So here is a junction, okay? This is junction, 3 lines. Parallel 63 and 189. So I got two answers for this and I also got an answer for this. 21 and 42. So the correct answer is this, adding these two together. So why can't we do 21 and 42? So they're asking us to find the voltage between A and B, right? Sorry, resistance between A and B. Let's say current comes from A. Is it the same current which goes through this and this? So they are not in series, right? Because two currents go through them. They are also not in parallel. Why? Although this point is common, they don't have the same other point, right? They don't have the same voltage in the other end. So we cannot add 21 and 42. We can add these two because they have the same voltage across them. So 21 does matter. We will see next. Okay. So we still don't know what to do with 21. We will do it, simplify it, and at the end we might be able to solve 21. So these are parallel. So 1 over 63, 1 over 189. So what is the answer we get? So we all have got 47.325. Okay, 47.25. So instead of these two, we can put 47.25, right? Okay, I'm going to redraw it. So I have this 42 and I have this 21. And here, now I have 47.25. So what can we do now? Is there anything in series or parallel? Any two resistors? So very good. 42 and 47.25, these two. Although I drew this wire in a weird way, these are one after the other, right? But the current which goes through this comes through this, right? Oops, sorry. This one. So they are one after the other. So these are in series. So I can calculate the REQ for 42 and 47.25. So what do you get? 89.25. Okay, let me redraw this. So I have A and B. And in between A and B, we have the 21, right? And now we have one resistor instead of these two. We have, sorry, this is like one junction, 89.25. So they are parallel to each other, right? Now we can simplify this 25. Before that, there was no way we can figure this out. Now we see that they are parallel to each other. So your final resistance will be, they are in parallel, therefore 21, 89.25. So when you do that, you get the answer as 17 ohms. So finally, you have one resistor between A and B, right? We have one single resistor between A and B, and it is 17 ohms. Okay, so always start from the easiest end and then work through it. They always give something that you can solve. So this doesn't have so many steps. It's just one step. But I want you to look carefully and figure out what this is. So I'll give a hint. Figure out the voltage here. Not the voltage. What is that point? Whether it is A or B. It is same as B, right? So if we look at this point, let's first look at this point. This point is common to all the three resistors, right? So for all the three resistors, one end is A. For this resistor, this end is B, and this end is connected to this end. Can you see it? They have just put a wire. We know this wire means nothing. It's same as these 2 points are connected, right? They are just the same point. So this point is same as this point. Can you see it? So it's a very confusing, tricky one. So for all the three resistors, one end is A, the other end is B. So really your resistors were actually like this. So this is your A and B. All three resistors has this N30, has this NA. All of the three has this NA. Let me draw it like this. So all of them has end, right? This end. And all of them has the other end connected to B. This end is connected to B, and this end is connected to B, right? All the other ends are connected to B. 30, 30, 30. So these are three resistors parallel to each other. So your resistance will be 1 over 30 plus 1 over 30 plus 1 over 30 inverse 1. So when you do that, you will get the answer as 10 ohms.